All right, good morning, everybody. Oh, yeah. So Canvas has this new feature called a quiz log, apparently. It's kind of nice. It has its pros and cons, like everything. Um, the one major con that I see that quiz log creating in math is if you guys use an outside calculator. So we'll have to play that a little bit by ear because if you were to use like GeoGebra or Desmos, it would show you exiting the quiz to use that. So just be aware that I'm already have that in mind if I were to use that quiz log. It does not show me what websites you go to, though. No, unfortunately. That would be super cool if it did, although that'd be a little bit scary as well because you'd really be tracked. It does not show me what websites you go to. It just gives me as a teacher a little bit of idea that if it wasn't like a graphing thing and I saw you leaving the quiz to go get extra help from it, that there is a problem in that area and I need to address that as a class. And if we think that someone is cheating or plagiarizing, I don't like the word cheating, then we can address that log if needed. But I I will not be looking at that log for every single assignment by any means. So I don't have the time to look at the log for 140 students for every single assignment. So please note that it's not something I'm going to be doing on a daily basis for you guys. I do. I know. A lot of people think I only have the one class that they're in, but I have six classes with about 140 students. So, yeah. All right. I hope everybody had a great break. I have my ways to keep up on it, so it's not too bad. Um, my break was uneventful. My entire family, minus my husband, he's the lucky duck there, had the flu. So we were down and out for about 8 of the 10 days, just laying on the couch, not doing much but watching TV. So even though it wasn't the greatest break, at least it was relaxing, I guess you could call it. Um, Although I do have to say it was a little hard getting up this morning, and I'm sure you guys can relate to that to get back into the swing of our routine of school here. So hopefully tomorrow goes a little bit better. All right, kind of on the agenda for the rest of the semester. Can you believe I just said the rest of the semester? We're going to fly through things pretty quickly here to wrap things up. We have lesson 4 today, and Thursday's class will take a look at lesson 5. Next week, we'll take a look at lesson 6. And then we have a review day or study day. I'll go over final exam details next week, Thursday. And then the week after that's final exams. So 2 weeks here until finals only. Any major questions with the pacing and the scheduling from here on out? I think they do have a mobile app. I don't use it, so I'm not too familiar with it. But I want to say yes, that Canvas does have a mobile app for you to use. Awesome. All right. Any major questions before we get started here today with 5.04? All right, then, if I remember correctly, we left off with 5.03 right before break, and that was our half angle identities. So if we, or our, not half angle, but our like sum um, angle identities, so we could add two things together to get from our unit circle to get a different value, like 30 and 45. We could then calculate 75 degrees, which wasn't originally on the unit circle. Um, that's where we kind of left things off, the sum and difference formulas. Um, Today we're going to go ahead and take a look at multiple angle identities. So we've got lots of identities in this next lesson here that we're going to need to take a look at. The first one is sine of 2u, cosine of 2u, and tangent of 2u. So this is different than what we've been dealing with because we've only really been looking at sine of x, cosine of x, and tangent of x. But now what happens when we take a multiple of that x next to our sine, cosine, or tangent there? So cosine is really kind of that special one. There's 3 different forms that we could use there as our identities. So the cosine 2u is going to be the same as 2 times sine u cosine u, but then cosine can be broken down into 3 different forms here. A lot of these look very similar to your Pythagorean identity form, so please don't get that mixed up. Notice it's a minus sign instead of a plus sign there. So there is a difference with these between the Pythagorean identities. So I'll give you a moment to copy that down. And we'll be constantly looking back at these as we look through our examples today. All right, so the first one is we need to prove this identity that sine of 2u equals 2 sine of u cosine u. So really what we're going to do is I can't use just the identity above because I am trying to prove that that is going to work out. So we're going to use our sum of sines. And instead of saying sine of 2u, let's write that as sine of u plus u. I think we all agree that 2u can be broken down into u plus u. And now let's use that that sum of sines to help us try to simplify this here. Does anybody remember what the formula is for sine of u plus u? Is it going to be one of each, like sine, cosine? Or is it, or is it sine, sine, cosine, cosine? Anybody remember the pattern that goes with the sine of u plus u? It's one of each. Yep, I just found it. So page 423, if you're looking for it in your book. So we would do sine u, cosine u, and then reverse it. But since the u and u are the same, when you reverse it, it actually looks the exact same, right? So because you have 2 of the same things, we're going to add the coefficients out front. So 1 plus 1 is 2, sine u, cosine u. And nothing else is needed because we now have that identity proved. So kind of a basic thing there to start us off this morning. Any questions with using that sum of sines identity there to help us prove that double angle identity? Okay, then we also have some identities called the power reducing identities. These you can use these if you need to get things lower than a 2 for your exponent. So if you have sine squared, cosine squared, or tangent squared, and it tells you to only write it in terms of sine, cosine, or tangent to the first power, this is when you would want to use the power reducing identities. Most of the time, I think it'd be okay to leave it in terms of sine squared, cosine squared, or tangent squared. It's really not that big of a deal. But if it does tell you that you have to write the answer with just a power of 1, then you're going to have to use these power reducing identities. All right, so here's an example where you need to prove an identity. You have cosine to the 4th theta minus sine to the fourth theta, and we need to get that to equal cosine of 2 theta. Notice that the exponent on this though is just a 1. So eventually along the way we're probably going to have to use these power reducing identities at some point. Maybe not right off the bat, but at some point we're probably going to have to rely on those. Alright, so when we're trying to prove an identity, remember we always start with the more complicated side, which is the left-hand side in this case. Any ideas on how we might be able to break down cosine 4 theta minus sine to the fourth theta? Any ideas there? Yeah, factoring. That looks a lot like the difference of squares. So we're going to go ahead and try to break that down using the difference of squares pattern for factoring. So that would be, let's see, cosine squared theta, or x, whatever variable you want to use there, minus sine squared theta times cosine squared theta plus sine squared theta. So everybody good with the factoring pattern to break this down using your difference of squares for step 1? All right, what do you notice once it's factored? Is there anything you can simplify with? Hopefully something pops out to you right over here. Oopsie, that's not my highlighting. Sorry about that, guys. Right here. What does this remind you of? Going all the way back to, I think, Unit 4 is where we first learned that. Yeah, that was your Pythagorean identity. The very first Pythagorean identity we learned was that cosine squared plus sine squared is equal to 1. Good. So at least we know we're multiplying by 1. So essentially that's just going to kind of disappear from the problem because you're multiplying by 1 there. Now is there a way I can change cosine squared theta minus sine squared theta? Yeah, we got to somehow get what's left here to equal the cosine 2 theta now. So, let's see if we can use those power reducing identities from above to see if we can get that to happen. So let's just start with the cosine squared theta. So cosine squared theta, we can go ahead and use this one right here. Now, I'm going to actually break this up a little bit. It's going to seem a little bit weird, but I'm going to do 1/2 plus 1/2 times cosine of 2 theta. Is everybody good if I just break this fraction up into a 1/2 plus 1/2 cosine of 2 theta? If I can do that, it's going to make it a little bit easier, I think, to notice the simplifying that has to occur if I can break it up like so. You cannot use a double angle identity because a double angle identity had, well, I guess you could if you're looking at the right-hand side. You could try to do that and get it. I think it probably does equal that right there. So yes, you definitely could do it that way. I'm just going to continue with the left-hand side though and show you that you'll get there using this one as well. But you could go ahead and use that cosine or that double angle identity over here on the right-hand side and then link them together, right? So you definitely could do that. I'm going to go ahead though and just show you using the power reducing identity. You can get there as well. Right? There's always more than one way to attack a problem in math, so kind of a pro and a con of it. All right, I'm going to go ahead and distribute the minus sign there. So when I distribute the minus sign, that's going to be a negative, and this is going to turn into a positive. You'll notice that the 1/2s are going to drop out, right? 1/2 minus 1/2 is 0. And then we do have cosine 2 theta and cosine 2 theta being the same, so you can add the coefficients out in front. 1/2 plus 1/2 is 1 cosine of 2 theta. So you can also get there using your power reducing identities too. Although I do like Tommy's way better, it's faster using your double angle identity. All right, questions with that at all? Okay, let's take a look at another one. It says rewrite cosine 4x in terms of trigonomic functions with no power greater than 1. So here is one of those examples where the problem actually says you can't have a power higher than 1. It was right here. Is this the one you are referring to? The negative sign? I distributed the negative sign through my second one. So originally I did have parentheses here, and this was a minus sign in here. But because I distributed the minus sign, that turned into a plus. Or distributed the negative sign, it turned into a plus there. So it was originally there, but we had to distribute it. Okay, good questions. Nope, you're not. Not at all. All right, let's go ahead and rewrite cosine 4 to the x. Any ideas how we would start this off? So cosine 4 to the x. We want to break it down. Yeah, essentially it's kind of like factoring. It's more or less rewriting cosine 4 to the x in terms of your squareds. Because if you can have something in terms of squareds, there's going to be an identity hopefully you can use to replace that. So let's rewrite cosine to the 4th as cosine squared x squared. Is everybody good with replacing that as cosine squared x squared? Essentially means the same thing. Okay, now to reduce that, let's use that power reducing identity. So instead of cosine squared x, we're going to use 1 plus cosine 2x all over 2 squared. And I guess we probably should multiply this out by itself, right? So instead of having the squared there, we can take this and multiply it by itself. Hopefully that will help. To multiply that though, really no easy way. We're going to have to distribute those numerators together. Let's see what we get when we distribute that. Obviously in the denominators when we multiply we'll get 4 there. But in the numerators we have 1 times 1. So 1 times 1 is just our 1. We'll have 1 times cosine of 2x. And then 1 times cosine of 2x. So because I have the same thing there, is everybody good if I just write 2 cosine of 2x for the middle term once we add the like terms together there? Does everybody feel comfortable at that spot? Okay, the last one though is going to be that more challenging one. What is cosine of 2x times cosine of 2x? Well, that is your cosine squared of 2x. So we were so close to getting rid of the exponents there to get our final answer, but we ran into a little bit of a road bump with that last term because now we've got a squared again. But that's okay. It looks like we're just going to have to use the power reducing identity, hopefully one last time. Now I'm going to break this up because it looks a little bit chaotic. So I'm going to do a 1/4 plus, now as I break up this middle term here, notice it's 2/4, so that's going to become a 1/2. So I just want everybody to kind of see what's going on there. And then you've got the 1/4 times cosine squared of 2x. So we've got to go ahead and use that power reducing identity on this last piece right here. So instead of having that cosine squared of 2x, we're going to do 1 plus cosine. Now here's a little bit tricky. Notice it says 2u. What exactly is the u in my last part here? Yeah, it's the 2x. It's your variable. So technically we're going to have a 2 times 2x in that last piece. Yeah, so that is going to turn into a 4x inside there. So we got to be a little bit careful with that last piece of substitution there, knowing that that u is technically that full variable of a 2x instead of just the x like it always has been in the past. Is everybody good with how we get that cosine of 4x then? Once I kind of rewrite everything here. So it looks like I'll have a 1/8 plus a 1/8 cosine for x and all that. If I want to, I can technically add these fractions together. I think that's going to be a 3/8. I'm running out of room. Eeks. Not the prettiest of answers, but notice that we do not have any exponents anymore, right? I know. And it's really crazy with all the fractions that are involved there, especially with the breaking part of this power reducing identity that we used. So it can get a little bit confusing in that process. Hopefully, though, you are able to follow along for that. Any questions with how I ended up with that boxed answer? All right, then there is one more set of identities to look at today, and that's your half angle identities. And half angle is just what you would assume. So sine of basically dividing by 2 with that x, so x over 2, and sine, cosine, and tangent. This time tangent is the finicky one. We've got 3 different routes that we can take for tangent. I like to use for tangent the first one because with the half angle identities for sine and cosine, you have to use the square root here. And for me, I think it's just getting into that same habit or remembering that same one helps for the tangent. So a lot of the times you'll see me kind of favoring the first formula if need be. Okay. I don't know if we technically need the half angle identities for this first example. We'll see here. It says solve algebraically in the interval from 0 to 2 pi. So notice that it does want us to solve for the x there. That means at some point in time, we're probably going to want to get it down to parentheses, right? Or factor it at some point, and then set each part equal to 0 and use the unit circle to help us solve for x. So when it does say to solve, remember you want to go kind of full circle there and use the unit circle to grab those answers at the end. All right, if it does say to solve, what would be your first plan of attack for this one? So you got sine of 2x equals cosine x. What would be your first plan of attack if you wanted to solve that? Any ideas? And two things kind of pop into my head. Yeah, so maybe starting with breaking down the sine of 2x using your double angle identities for sure. So I'm going to go ahead and follow Tommy's plan of attack by rewriting the sine of 2x as 2 sine x cosine x. I still would then have that equal to cosine x on the other side. So what would become my second step in the problem? Think back to your Algebra 1 days even. If you had to solve a polynomial, what would you need to do in order to solve it? So even if sine and cosine wasn't in there, what would you have to do to try to solve it? Put everything on one side. We have to use that same plan of attack with the trig. So we've got to make sure we move that cosine x to the other side. So that would be my next step, is subtracting cosine x from both sides. Okay, because you want it to equal 0 before you can go and start factoring if need be. Speaking of factoring, is there a GCF we can take out from those terms? Yeah, cosine x. So I'm going to go ahead and take that GCF out of cosine x. That means we'd have a 2 sine x minus 1 left over. And now we're to the point where we can break it into the two separate pieces. So let's start with cosine x equaling 0. Where does cosine of x equal 0 on the unit circle? So grab those unit circles. Where does cosine of x equal 0? At pi over 2 and 3 pi over 2. Good, and those do fall in the interval from 0 to 2 pi, so we're good there. The second piece of information then comes from what's inside the parentheses. So 2 sine of x minus 1 equals 0. We're looking for where sine of x is going to equal 1/2, right? Because you add 1 and divide by 2. Where does sine of x equal 1/2 on the unit circle? Pi over 6 and 5 pi over 6. Awesome. So technically we got 4 answers here that are going to work for this problem. So our 4 solutions would be pi over 2, 3 pi over 2, pi over 6, and 5 pi over 6. Awesome. Any questions with how we solved that one? I know, right? There's a lot of identities. All right, let's go ahead. And I think this next one actually will use the half angle identity possibly at some point. We'll take a look here. The good news is I think there's only 2 more lessons after this one, right? And I don't believe that there's going to be anything too lengthy that goes along with the last 2 lessons. I actually like the last 2 lessons compared to this one. It's a little bit easier to visualize what's happening with lessons 5 and 6. So something to look forward to there. Okay, so solve this one right here. What would you try to do if you saw this one on a homework assignment and you saw that term solve? What might you try to do for this one? Again, two things kind of jump out at me right at the beginning, so you kind of have a couple of choices to begin. Using the half angle identity for sine u over 2 right here, this piece. Okay, and I'm going to highlight that so that we're not losing part of the problem with it because there's technically a 2 out in front. So that piece right in there. All right, I'm going to go ahead, take Tommy's advice, and we're going to replace that sine squared of x over 2 with plus or minus, it looks like, the square root, square root of 1 minus cosine of x all over 2. Now notice that it was squared, so technically that's going to be squared. All right, so what's going to happen with that plus or minus square root sign if that whole thing is squared from that exponent there? Yeah, it's going to actually disappear, right? We're going to use the positive root of it because you're squaring it, so obviously that's going to stay positive. But that square root and the squared are going to cancel each other out. And that just became a lot better looking without the square root sign in there, right? So notice the squared did get rid of the square root sign in the problem because I don't have the sine squared of u over 2. It's just sine. So I do have to take that squared into consideration there, and that's going to cancel out that square root sign. I also is going to cancel out the 2 over 2. So I can go ahead and get rid of that. And now we're all the way down to just this. All right, any other ideas for me moving forward once we get to this spot? So that half angle identity actually turned out quite nicely when we needed to simplify on that right hand side. What about sine squared x? Can we break sine squared x down? Maybe we can try to turn that into something with a cosine. We could maybe use a power reducing identity. We possibly could do a power reducing identity there. I'm wondering if it would be easier to use a Pythagorean identity instead. Yeah, let's do a Pythagorean identity with the sine squared x instead of the power reducing one. Although I think the power reducing formula would probably get us to the exact same point that the Pythagorean identity would, but we might be a little bit better off using the Pythagorean identity and replacing that with the 1 minus cosine squared. Only because I can kind of use the same factoring patterns that I have in the past, right? So once I replace that with the 1 minus cosine squared x, I can start getting everything to one side. The ones are going to disappear, it looks like. So then we're left with a cosine x. I'm going to just start with the positive piece of it. A cosine x minus a cosine squared x equals 0. Any questions with that one so far, I should say? Because now we're at that point where we can take out the GCF. What is the GCF that we have left at this point? A cosine x. Remember, the end goal was to solve here. So we have, where does cosine x equal 0? Cosine x equals 0 at what spots on the unit circle? Pi over 2 and 3 pi over 2? Okay, there's a method to my madness with leaving some space after here, and I'll come back to how we're going to fill that empty space in. It looks like the next piece would be, where does cosine of x equal a positive 1? Right? Because if I take this and then set that equal to 0, you can add cosine of x to both sides. So where does cosine of x equal 1 on the unit circle? And there should only be one spot at it. 0? All right. Now, it doesn't say to solve within a certain interval, right? Notice that it just says to solve. So because it doesn't have within the interval, we've got to add a little bit extra pieces to our answer. And what I'm going to do to add to our answer is just put a plus 2n pi after each one. Now, why am I going to put a plus a 2n pi after each one? Or technically plus or minus, I could say. Yeah, remember that 2n pi is just multiples around the unit circle. So if I were to add 2 pi to pi over 2, you end up in that same spot every time you go around, right? So one revolution around, bam, we're back in that spot again. Another 2 pi around, bam. Or if you subtract it, you end up in that same part. So if it just says to solve and it keeps it generic, we do want to add a plus minus 2n pi at the end of all of those answers so we can take into consideration the multiple times around the unit circle to get to that same spot. So some of your answers, you might notice that extra piece of information thrown in there. Questions with this one at all? Right. So the only time that you won't see a 2n pi is if they're using tangent. So if we were using tangent instead of cosine or sine at the end here, they might just use plus or minus an n pi, because if you think about it, tangent is going to be equivalent to itself exactly halfway around the unit circle, right? So if you find a tangent marker, like do maybe pi over 4, halfway around the unit circle, tangent is going to have that exact same value at negative pi over 4, right? So negative x, negative y, that's going to be the same result that you had in quadrant 1. So the only thing that's going to differ a little bit is if you were to see a tangent here at the end. Then they only use a plus or minus n pi to get that answer. So technically you only have to go halfway around the unit circle to hit an identical value there. But just to play it safe, even if you have tangent here, if you were to put plus or minus 2n pi, that's okay. You just got to list both of the tangent answers then. So as long as you have both of the representations for tangent, and if you put that plus or minus 2n pi, you're basically kind of playing it safe. And you're going to have a correct answer there. So, but in case you have like a multiple choice question and you see just an n pi, that's why, because they're dealing with tangent at some point. So good questions. Any other questions that deal with these? Otherwise, I think we can maybe sneak in one more example here. All right, do we want to look at a proving an identity one or a solving one? I think I've got a couple options that are left. A solving one, okay. Find all the solutions. This is my only solving one I had left though. Find all the solutions to the equation in the interval from 0 to 2 pi. All right. Any ideas what we would do with this one? Sine of 2x equals 2 of sine x. Remember, our goal is to solve this, not to prove it, to solve. Yep, that could be definitely one step. So let's move everything to one side. So I guess I will just subtract the 2 sine x. What's the next thing that catches your eye now that you have it set equal to 0? The next thing that should catch your eye, not cut your eye. Yikes, that would be pretty bad if it cut your eye instead of caught your eye, right? Is the double angle identity. Yeah, so technically you can't take out a GCF of a sine x if you have a 2x in there. You've got to rewrite that using a double angle identity. So sine of 2x, I believe that's just your 2 sine x cosine x, correct? So taking a look back at that double angle identity there. Now you should see a GCF pop out to you. What's the GCF that stands out? A 2 sine x, good. So I'm going to take that GCF of a 2 sine x out. When I do that, it looks like we have a cosine x minus 1 left over. And now you've gotten to the point where you can separate each part and solve. So we'll start with the 2 sine of x. 2 sine of x equals 0. If you divide both sides by 2, you're looking for where sine of x equals 0 still. So where will the sine of x equal 0? And we are looking at a certain interval here. At 0 and pi. Okay. And now I'm going to go ahead switch gears. Let's go ahead and take a look at cosine x minus 1. Add 1 to both sides. Where does cosine of x equal a positive 1? At 0, and it's already listed there. Notice that we don't want to put 2 pi down because of the parentheses that's used. So that 2 pi means we don't want to include it in our answer because we're already taking 0 into account. And 0 and 2 pi are at the same spot. So we technically only have 2 solutions for this one, 0 and pi. Questions with that one? It's a lot to keep straight, right? And it's all in the details, and that's where we seem to get a little bit confused and we forget all the little small details, right? Like the difference between a bracket and a parentheses. So bracket, yes. Parentheses, no, don't include it. I like to think of the bracket as more of a hug, I guess. Like you're bringing it in close, you want to include it, so it has like arms that's bringing it in. The parentheses, it's like, yeah, no, I'm going to push you away. It's like a bumper more. So think of your bracket as like hugging it in, bring it closer, you want to include it. Parentheses like, yeah, no, you're okay from a distance. You can stay out there. I don't really want to bring you in and include you. All right. any other major questions with all these identities? So this lesson can seem a little bit overwhelming just because there are so many more identities that were thrown into the mix. Okay, well, the good news is that we made it through our first day back. Wasn't a very pretty lesson our first day back, but we did make it through nonetheless. So that's always good. I promise you that Thursday's lesson will not be as bad as today's. So I promise you that the last two lessons of the semester are going to end on a high note. So I promise you. All right, that's all I got for your Tuesday back. Hopefully, you have a great rest of your day. Get back into your old routine. And I will see you guys all again Thursday. Bye, everyone.